In this video, I'm going to work through 4 different calorimetry problems. I would recommend that as you see the problems, you stop the video and try to work them yourself, or stop, read the question and see what the variables that were given to us are, and think about it a little bit before you watch me work through it. That's my recommendation. Take it or leave it. So in a calorimetry problem, we have a general starting point in every case, because in calorimetry there is a transfer of thermal energy. So we use this idea that the heat of the system is equal to the negative heat of the surroundings. What is heat? It's the transfer of thermal energy. So this thermal energy is going between the system and the surroundings. If the system is giving off heat, the surrounding is absorbing it. If the system is absorbing heat, the surrounding is giving it off. Now I have students ask me all the time, does it matter which side I put that minus sign on? Well, no. If I were to divide both sides by -1, that would transfer it over here, or multiply both sides by -1. It doesn't matter, but I generally write it this way. Now the system might be a reaction. It might be an object heating up in terms of its temperature or cooling down. The surroundings is generally going to be something that's heating up, raising in temperature, or lowering in temperature. Now when something changes temperature, the next thing we need to realize is we can determine its heat transfer with this equation. The mass of the object that's changing temperature, its specific heat capacity, and its change in temperature. If we aren't given the mass and the specific heat capacity, we might be given the heat capacity. And heat capacity, I abbreviate without the sub S, and specific heat capacity, I'm using a C sub S. So it depends between these two whether or not you're given mass and the specific heat capacity, or just the heat capacity, to decide which one of those two you use when the temperature of an object is changing. So let's see how these play out in these problems. In this problem we have methanol. It is undergoing combustion, and it happens in a constant volume bomb calorimeter. That's what we use bomb calorimeters for, is combustion reactions. So we get our starting point that the Q of the system is equal to negative Q of the surroundings. Well, when a reaction is involved, I usually call that the Q of the reaction. The Q of the system is the reaction. I call the system the reaction. And the surroundings is the bomb calorimeter. Now sometimes they break the surroundings up into the water versus the bomb, but in this case they tell me the heat capacity of the bomb and its water. So I will consider the surroundings, okay, the whole bomb plus its water. That's what's surrounding the bomb that's what's surrounding the reaction. So what is the reaction? The reaction is methanol burning, okay? So combustion. What's the surroundings? It's the bomb and the water. Now we want to know the heat of combustion. That's what it says. What is the heat of combustion? That is the Q of the reaction. Combustion is the reaction. So I want to know what this is. So what I need to know is what this side is. Now, the bomb and the water are changing temperature. They're rising by 4.20 degrees. Now, it's just saying that the water rose by that, but the bomb has to rise too by the same amount. It's just that the thermometer is sitting in the water. So which of the two would I use? Well, I'm given heat capacity, and remember, heat capacity is this bottom one. So I just need the heat capacity, which is 10.4 kilojoules per degree Celsius, and I need the change in temperature. Well, they didn't give me the final and the initial, but they did tell me that it rose by 4.20 degrees Celsius. So it's this part that equals Q, and the minus is just coming along for the ride. So the Q of the reaction, when it took place in this bomb calorimeter, is equal to a negative 43 0.68, and the units would be kilojoules. Well, when I look up here, it says molar heat of combustion. This is just the heat of the combustion reaction for the amount that I put in there. If I want to know the molar heat of combustion, I need to know how much for 1 mole. That's what molar heat of combustion means. Like molar mass means the mass of a mole. Molar heat of combustion means the heat of combustion for a mole. So I'm going to figure out if I have 1.922 grams of methanol, I need to figure out how many moles that is. So that's what I'm doing here. I'm going to convert to moles. The molar mass of methanol is 32.05. So I'm adding up the carbon, the 4 hydrogens, the oxygen, and I get that value. So the moles of methanol is 0.05997. So that's how many moles of methanol I have. So if I want the molar heat of combustion, I will take the heat of combustion for the amount given, and I will divide by the amount I combusted in units of moles. And that will give me the answer of a negative 728 kilojoules per mole. So that's one type of calorimetry problem. Let's go to the next one. In this next one, I read along, and pardon me while I rip paper out here. This next one, I see there's no reaction. Stop and read it and see what I'm talking about. There's no reaction. There is a stainless steel ball that is being placed into water, and both objects are changing temperature. But we have the same starting point. The Q of the system is the negative Q of the surroundings, but in this case the system is not a reaction. I'm going to choose to make the system the stainless steel ball, so I'll call it SS for short, stainless steel. That stainless steel ball bearing is placed into water in a calorimeter. Okay, it says it's being put in a constant pressure calorimeter containing 120 milliliters of water. So it's basically the water. Now, it probably should say in this problem to assume the heat absorbed by the calorimeter is negligent, because it doesn't mention anything about the calorimeter. It's just talking about the water. So we're assuming that the calorimeter is just being a good insulator to keep the heat going anywhere else. Since the stainless steel ball bearing is changing in temperature, and they give me the mass of it, okay, then I would assume I'm going to use the MC sub S delta T form of this equation. So I'll do that for the stainless steel ball bearing, and I will do the mass, the specific heat capacity, and the change in temperature for the water. Now let's lay those values in there. It's 30.14 grams of the stainless steel ball. It tells me the specific heat capacity is 0.474 joules per gram degree Celsius. And it's not giving me a change of temperature, it's giving me a final to look for. I'm going to call this, let's just call it X, okay? That's my final temperature. I just don't want to write that every time. So that's my X, that's what I'm looking for, minus the initial temperature, 117.82 degrees Celsius. And on the right side, I have the mass of the water, which if it's 120 milliliters and the density of water is 1 gram per milliliter, 120 milliliters is 120 grams. Specific heat capacity is given 4.184 joules per gram degree Celsius. Final, I'll call that X. Now that has to go to the same final temperature. They exchange heat until they reach the same temperature, minus its initial temperature, and it was where is it? 18.44 degrees Celsius. So now I've laid it out and I have one unknown, and that's x. I would recommend you try to solve for x without watching me do it. But if you get stuck and you don't get 21.19, then I will show you how I did it. First thing I'm going to do is I'm actually going to just get this part. Negative 120.0 grams and 4.184 joules per gram degree Celsius. I'm going to divide both sides by that value, minus 120 grams and 4.184 joules per gram degree Celsius. The good thing about doing this is, well, it all cancels on this side, right? And on this side, the grams are canceling and all of these units are canceling. Okay? And when I take 30.14 times 0.474 and divide by 120 and also divide by 4.18 and also the negative 1, I end up with a negative 0.02845. All the units are canceled. And that would be times x minus 117.82 degrees Celsius. And on the right side, I am left only with x minus 18.44 degrees Celsius. On the right side, I'm going to do the distributive property. When I take this and multiply both terms by it, I end up with, let's see, 3.352 degrees Celsius. That's me taking the 0.02845 and multiplying by, and that's a negative, by this negative number, and those combine to give me this degrees Celsius here. And then I'm going to take this times the first term. I just switched them around because I think it looks neater. Nothing more. 0.2845. Okay, so this is x. It's multiplied by x. And that is going to give me x minus 18.44 degrees Celsius. Now I'm ready to get my x terms together and my degrees Celsius parts together. So I'm going to bring the degrees Celsius to the left side, and that would be 3.352 degrees Celsius plus 18.44 degrees Celsius. And on the right hand side we have x plus 0.02845x. When I add those two numbers together, I get 21. Well, I can't make it work. 21.79 degrees Celsius is equal to 1.02845x. Now I'm running out of room here, so let me just describe what I did next. I divided both sides by the 1.02845, and that leaves me with an x equal to 21.19 degrees Celsius. And that is the answer to the question. The temperature that will be reached needs to be somewhere in between the temperature of the water and the temperature of the stainless steel ball. Because it takes a lot more heat to raise 1 gram of water by a degree than it takes to raise the stainless steel ball by a degree, it ends up being a whole lot closer to the temperature of the water than it does the temperature of the stainless steel ball bearing. Plus, I had a whole lot more water as well. In my next problem, it's again a combustion reaction. It's similar to the first one that I did, actually, except they're asking for the heat given off by the burning magnesium in two different units, either kilojoules per gram or kilojoules per mole. So once again, the Q of the reaction is equal to negative the Q of the surroundings. The reaction is the burning of magnesium. And I should have said the Q of the system. I'm sorry, I jumped ahead of myself. Q of the system is negative Q of the surroundings. The system is the reaction. The reaction is burning, okay? Magnesium is burning. That means it's reacting with oxygen. And that is going to be equal to the negative Q of, well, what's surrounding this thing? It's the bomb calorimeter. Okay? So I'm going to call it the bomb calorimeter. The Q of the reaction is just brought down. The Q of the bomb calorimeter I'm going to replace with C delta T because they gave me the heat capacity and the change of temperature. So the heat capacity was 30, 24. Be careful that you bring down the units. The temperature change, well, it was increased, so it's a positive number, by 1.26 degrees Celsius. So the Q of the reaction is equal to a negative 34.05 joules because the degrees Celsius cancels. But once again, this is the energy for only this many grams of magnesium combusting. Okay? We want it for a gram. We also want it in kilojoules and not joules. So let's go ahead and do that part. I don't want joules, I want kilojoules. So that's going to be a negative 3.405 kilojoules. And if we take that negative 3.405 kilojoules and divide by how many grams we have, which is 0.1375 grams, we get this value in kilojoules per gram, which is a negative 24.76 kilojoules per gram. But we also want it in kilojoules per mole. And so we will take this grams and not stop there. Go and say, I don't want grams, I want per mole. And we look at the periodic table for magnesium, and it's 24.305 grams in a mole. And that will give me a negative 602 kilojoules per mole. And I'm sorry for those little lines that keep popping up between there. It's driving me nuts. It's got to be driving you nuts too. Negative 602 kilojoules per mole. Well, why are these written up here as positive numbers? Well, that is just a very subtle language thing. The Q is negative. Okay? It is an exothermic process. The Q is negative. So they said calculate Q of the reaction. We have done so. But notice the way it's worded. Calculate the heat given off by the burning. So we know that if Q is negative, it's given off, and that's how we word it. We are giving off 24.76 kilojoules per gram of magnesium, or we are given off 602 kilojoules per mole of magnesium. You don't say you're giving off a negative 602. That's just being redundant, and it's, like I said, it's just a language thing. Okay, this next problem is quite different. In this next problem, we are trying to determine the heat capacity of the bomb. In our previous problems, we were told what the heat capacity of a bomb calorimeter was. Well, how do they know this? Well, they have to standardize the bomb by doing a reaction that you know the heat for. And that's what's going on here. They are burning benzoic acid, and they're seeing what the energy is for the benzoic acid, and that's up here with the negative 26.7 kilojoules per gram. So the Q of the system is equal to the negative Q of the surroundings. That's always my starting point. And the system is the reaction, and the surroundings is the calorimeter. Now in this case, we can determine the Q of the reaction because we know the heat Q of combustion, that's the reaction. It's in kilojoules per gram. But I don't want to put in a negative 26.45 kilojoules because that's per gram. How many grams am I actually doing here? I'm actually doing it for 5 grams. So to get the Q of the reaction, I'll take the negative 26.45 kilojoules per gram, and I will multiply by how many grams I have. And that will give me the heat of the reaction that I'll want to plug into this value. It will be, I have no idea. I got to turn my page. Excuse me. Okay. It'll be a negative 132.3 kilojoules. So that's what I'm going to put in for this, a negative 132.3 kilojoules. So what am I going to put in for the calorimeter? Well, I'll bring down my minus, and in place of the Q of the calorimeter, I'm going to replace it with C delta T, because I want to know the heat capacity of the calorimeter. Well, let's go ahead and replace this delta T with what they tell me. The temperature rose by 4.90 degrees Celsius. So a negative 132.3 kilojoules is equal to a negative C times the 4.90 degrees Celsius. So I divide by the 4.90 degrees Celsius on both sides. And the minus. Might as well get rid of that minus too. Negative 4.90 degrees Celsius. And that will give me the heat capacity of the bomb calorimeter, which is 27.0. And what are the units? Kilojoules per degree Celsius. So this is not an exhaustive list of things that you can do with calorimetry. You've got lots of practice with sapling and so, but I wanted you to see how the process plays out over and over again. Starting here, making sure you divide out, if something is changing temperature, you replace it with either C delta T or M C sub S delta T. If it's a reaction, that's your system, but there's not always a reaction. So look at these and see the similarities between them and see how they're all very much alike. You're just solving for different variables.